The third method that we will learn is Van Everdingen Hurst Unsteady state model. So we learned about steady state before. So steady state is an ideal state, ideal model. But reality, sometimes we cannot get a steady state. So most of the time it's unsteady state. So Shelter's model cannot be used when the aquifer influx is in an unsteady state condition. So however, this unsteady state is typically, so most of the time in the field it will be unsteady state. So that's why we have to use the Van Everdingen-Hurst model. And this model is applicable for both edge water drive, which is this diagram, and bottom water drive, which is this diagram. So edge water drive means that if you have an aquifer reservoir, so this is your gas cap, this is your reservoir cap. Like this, you have your oil here for a bottom water drive. But for edge drive, your oil will be here. That means your water will be on the edge here. So the water will be on this edge here. So it's like a rainbow shape. And this middle will be just rock, formation rock, without any oil or gas or water. So this part is this diagram. So edge water drive, you only have oil water contact on this part, and you have to dig your oil well. You can do here one oil well and this oil well, also this one. But for bottom water drive, the whole bottom is water. So the oil will be just on the top here, not like you don't have this shape right here. We also need to consider the radial aquifer, which is the shape like a circular shape, angular shape like this. So if you have a circle, it's like a pie, you have an angle here. So there will be a reservoir that shaped like radial, and also the normal linear reservoir, linear aquifer. So this is your oil and this is your water. So there's different shape of reservoir and water aquifer. For the radial aquifer system, if you imagine this is from the top view, so from the top you can see that your oil is in the middle and your water is surrounding the reservoir oil formation here. So this is from plan view showing the reservoir aquifer system. So the radius here is your reservoir radius RR, which is from the center of your oil reservoir towards the boundary of this. So this is called RR. And your RE is the radius from the middle, towards the end of your water aquifer boundary. So if you have your water here, the RE is from the middle to the water boundaries. For a linear reservoir, it's simple. If you have, this is the cross section from the side. This is if you look from the top, and this is if you look from the side. So if you cut the cross section of the reservoir, you can see for a radial reservoir, your oil will be in the middle and the water will be flowing both sides, or maybe if from the other side too, towards your reservoir. And this will be your oil well. So you can dig like that. So Van Everdingen solved the diffusivity equation for radial flow of water across the oil-water contact boundary RR. So RR is oil-water contact from the oil towards the water only. And this equation is known as the diffusivity equation. So this will be at a constant pressure. And the equation is made dimensionless to make the calculation easy, so there's no unit. So how do we make properties like time and pressure? Time has unit in second, hours, and pressure we have PSI. We need to convert this unit to become no unit. So no unit means dimensionless. So these properties, this constant has to be dimensionless for us to use the diffusivity equation. So to make it dimensionless, we're gonna use this equation. We introduce a new time which is TD, dimensionless time, and it is 2.637 times 10 to the power of minus 4 kT over porosity mu Ct Rr squared. So we have all of these: permeability, time, the porosity, the viscosity, the compressibility of total, and also your radius. And then we're gonna calculate the dimensionless radius, which is Rd. So d dimensionless. We have the radius and also the oil contact radius here, Rr. And then we have dimensional pressure, P minus P reservoir, Pi minus P reservoir. So using these three new dimensionless constant, we're going to solve this diffusivity equation. So you have initial condition, which is Pi and R at t equal to 0. And you also have the boundary conditions. So boundary is the final value. So P equals to Pi minus delta P. So the first value is Pi, and you, for example, you have delta P here. So Pi plus the first pressure increase, which is P1. So you have P1. And then P1, and you have your second pressure increase, you'll get P2. And so on until Pn plus 1. So it's like an increment. That's what they call the boundary condition. And then you have finite Aquifer and infinite Aquifer. So finite means the boundary is clear. You have a value for that boundary. For example, your radius is until Re. So Re is a value that you know. But if you have infinite Aquifer, you don't have your boundary, and we assume it's to be infinity. So you don't have your radius. In radius, you assume it's as infinity. So for solving equation 5 in terms of dimensionless water influx, you will have this new equation. So the water influx is U. U is the water influx constant times delta P times WED. Delta P is the pressure drop and WED is water influx for dimensionless. So to compute this equation, you need to determine these three things. Okay, for U, it depends on the shape of the aquifer. So first, if you have radial aquifer, you will have your angle. So you just have to put this in the equation. So U equals to 1.119 porosity times compressibility total radius squared times height of the reservoir times the angle of your aquifer over 360 degree. So just plug into this equation. To calculate U for a linear aquifer, just use this equation, it's the same. For dimensionless water influx, so it can be a function of dimensionless time and dimensional radius. This can be achieved by a table or from the graphic form. So as you can see, the graph here show the aquifer value of WED, T over TD, dimensionless time, and the ratio RE over RR. So asymptote means steady state value. The maximum will be your WED, and WE max equal to U delta P WED max. So from the graph here, you have WED of and the axis is dimensionless time. So you can see from the graph here the different value of RE over RW, and you can just for example, you have RE over W of 4, and then you have your time here, TD. So you just read the graph like that, and you will get the WED, which is 6 for this case. So for radial aquifer, the maximum WED is RD squared minus 1 over 2. And for the linear aquifer, the WED max will always be 1. This is because your RE over RW is the same value because there's no radial angular radial. So that's why for linear, it's always 1. For the graphic solution, this is determination of dimensional water influx WED. I have shown you in the previous slide. So you just have to plug in, find your TD in the graph here. For infinite aquifer values of dimension influx, WED, for values of dimensionless time TD. This graph is also showing the same methods on how to find your WED. So you just read the graph here. For a tabulated solution, you can calculate your TD for different RE over R here. You have 1.5, 2, 2.5, 3, 3.5, 4, 4.5. And it's the same like the graph. You just read your TD here. If you have 1.3 TD, you can check RE over R. If you have 3 for RE over R, that means your water influx is dimensionless time here is 1.25, your fluid influx is 1.7. So it's the same like the graph, you just read the dimensionless time and you'll get your WED. And this is the same. So the third is the step pressure, delta P. So this is a bit hard to learn. So for example, here we have 3 different time. So we have t equal to 0, the initial time, t equals to t1, the first time, and t equal to t2, the second time. So the step pressure means at every addition of time, you have the delta P. So for t equals to 1, your P1 will be equals to Pi minus delta P1. And WED is 0, WE at t times 0 is 0 because it's 0. For WE at t equals to 1, you have some value here. And then for t equals to 2, you have the value from the previous year plus the value of the second one. So for more understanding, if you can imagine this as steps, tangga, that will be easier to understand. So this is the plateau pressure. So it is arithmetic mean. So arithmetic means, for example, it's just addition, summation of things. So for plateau pressure, this is Pi plus P1 over 2. And at the second step is P1 plus P2 over 2. So this first number will be the last number from the previous calculation. And then it will become P2 plus P3 over 2, P3 plus P4 over 2. So this is known as delta P1, delta P2, delta P3, and delta P4. So plateau pressure 1, plateau pressure 2, 3, 4. So delta P, your delta P1 will be plateau pressure 2 minus plateau pressure 1, which is this one, if you can understand it. So I will give you some example for this so you can understand more, and mostly we will be using Excel program because to manually calculate this will be a bit hard because there's a lot of numbers that you need to plug in, but I hope you can understand this concept.